The discovery of 55 Cancri A was one of the most exciting breakthroughs in modern astronomy. In 2004, a team of astronomers identified this strange world orbiting a star about 40 light-years away. Its existence was confirmed through advanced observation methods that allowed scientists to detect subtle changes in the light of its parent star. At first, no one realized just how unusual this planet would turn out to be, but soon it became clear that this was far from an ordinary exoplanet. The planet belongs to a system known as 55 Cancri, which contains several worlds orbiting a bright star. This system instantly became a hotspot for scientific research because of its diversity of planets. The detection of 55 Cancri E required patience, precision, and cutting-edge technology. Scientists relied on the slight wobble of the star to confirm the presence of the planet. Every small signal had to be carefully analyzed to rule out errors. The results revealed an incredibly dense world that defied expectations. From the start, astronomers knew that 55 Cancri E was special. It orbits its star extremely closely, completing one full revolution in less than a single Earth day. This means the planet is subjected to intense radiation and heat. Despite these extreme conditions, its density suggested a rocky structure rather than a gaseous one. This intrigued scientists, since most close-orbiting planets were expected to be gas giants. The unusual readings hinted at a composition unlike anything found in our own solar system. The more researchers studied the planet, the more questions arose. How could such a dense, rocky body survive in such a hostile environment? What processes could have led to its formation so close to its star? These mysteries drove scientists to examine its composition with greater detail. Over time, new data would reveal extraordinary possibilities about its internal structure. But even before that, the nickname Super Earth was attached to 55 Cancri E, emphasizing its unusual nature. The use of telescopes such as NASA's Spitzer and later the Hubble Space Telescope helped refine measurements. These instruments provided insight into the planet's atmosphere and temperature variations. They also allowed scientists to collect light curves that indicated chemical signatures. Each new piece of information brought astronomers closer to understanding this enigmatic world. The tools of modern astrophysics became crucial to piecing together its hidden identity. One of the most striking things about 55 Cancri E is its sheer proximity to Earth in astronomical terms. At only 40 light-years away, it is practically a neighbor in the galaxy. While it is still far beyond human reach, it is close enough for detailed observation with advanced technology. This makes it a key target for studies about exoplanets and their formation. The planet became one of the best-studied super-Earths discovered to date. Another reason this discovery was so impactful is the fact that 55 Cancri E belongs to a multiple-planet system. This allows astronomers to compare its properties with those of its siblings orbiting the same star. Such comparisons are invaluable as they help scientists test theories of planetary evolution in varied conditions. The presence of both gas giants and rocky worlds in the same system raises questions about diversity in planetary formation. This makes 55 Cancri a natural laboratory for studying exoplanets. The discovery also carried cultural and scientific weight. Media outlets quickly picked up the story, highlighting the potential for something extraordinary beneath its surface. Scientists, too, were fascinated by the idea of a planet so radically different from our own. With every study, the speculation grew stronger. Could this planet actually contain something as precious as diamonds? This question would transform 55 Cancri A from a scientific curiosity into a worldwide sensation. For researchers, however, the discovery was more than just sensational headlines. It provided critical data about the range of possible exoplanetary compositions. 55 Cancri E challenged traditional models of rocky planets. Its density and orbit defied expectations, forcing scientists to rethink assumptions about planetary systems. This shift in perspective opened the door to new theories about how planets form and evolve. In this way, its discovery was as transformative scientifically as it was culturally. Ultimately, the discovery of 55 Cancri E marked a turning point in the study of exoplanets. It showed the incredible diversity of worlds that exist beyond our solar system. It also reminded us of how little we truly know about the universe. What began as a detection of a faint wobble in a star's light grew into one of the most fascinating astronomical stories of the century. And this was only the beginning, because what scientists would propose about its composition was even more astonishing. Why it is called the Diamond Planet. The nickname Diamond Planet was not chosen at random. Scientists noticed that 55 Cancri e had a density that suggested a carbon-rich composition. Unlike Earth, which is primarily made of silicates and oxygen-rich minerals, this planet appeared to be dominated by carbon. If true, this would mean its interior could contain massive amounts of crystallized carbon, possibly in the form of diamond. This bold hypothesis quickly captured the world's imagination. Diamonds form under extreme pressure and heat, conditions that exist in abundance inside massive planets. In the case of 55 Cancri e, its intense gravity and scorching environment make such processes plausible. The idea that a whole planet could be filled with diamond-like structures was revolutionary. It painted an image of an entire world sparkling with unimaginable wealth. While this was mostly theoretical, the very possibility made headlines worldwide. The concept was based on detailed models of the planet's composition. By combining mass, size, and density measurements, scientists could infer what elements might dominate its interior. In the case of 55 Cancri e, these numbers matched predictions for a carbon-rich world. This stood in stark contrast to Earth, where oxygen bonds with silicon to form rocks and minerals. Instead, 55 Cancri e seemed to follow a completely different recipe for planetary formation. Media outlets quickly spread the name Diamond Planet, making it one of the most famous exoplanets ever discovered. The idea resonated not only with scientists, but with the general public. Who could resist the thought of a planet made of precious gemstones? The nickname added a layer of wonder to the scientific discovery. It transformed technical data into a story that captured people's curiosity worldwide. Yet despite its appeal, the Diamond Planet theory is not universally accepted. Many scientists caution that the evidence is still indirect. The chemical composition of 55 Cancri e is difficult to determine with certainty. Its proximity to its star makes observations challenging. Without direct sampling or more advanced data, the diamond hypothesis remains speculative. This highlights the balance between exciting theories and the cautious nature of science. Nevertheless, the possibility remains intriguing. If the diamond hypothesis is correct, it would mean that planetary formation is far more diverse than previously thought. It would prove that nature can produce exotic worlds with unimaginable internal structures. Such discoveries remind us that the universe often exceeds human imagination. Even if 55 Cancri e is not entirely made of diamond, the fact that it might be is enough to inspire wonder. The Diamond Planet theory also sparked discussions about the economic and cultural implications. If humanity ever gained access to such a world, the abundance of diamonds could alter the very meaning of value on Earth. What was once rare and precious could become common. This raises philosophical questions about wealth, scarcity, and human desire. Though entirely hypothetical, these ideas show how science fiction often emerges from real scientific theories. From a scientific perspective, the Diamond Planet nickname emphasizes the role of carbon in planetary science. Understanding how carbon-rich planets form can reshape our models of planetary evolution. It also helps us appreciate the variety of conditions under which worlds can exist. In this sense, the nickname is not just catchy, it reflects a real scientific debate about the building blocks of planets. What makes the story even more fascinating is how it connects science with human imagination. The Diamond Planet symbolizes both the rigor of astrophysical research and the allure of mystery. It bridges the gap between technical data and cultural storytelling. This is why 55 Cancri e remains one of the most iconic exoplanets in modern astronomy. Ultimately, the name Diamond Planet serves as a reminder of why we explore the universe. It shows how discovery is not only about data, but also about inspiration. The idea of a glittering world made of diamonds may or may not be real, but the curiosity it sparks pushes us to keep searching. And that, perhaps, is more valuable than diamonds themselves. How scientists determine the composition of exoplanets. One of the greatest challenges in modern astronomy is figuring out what distant exoplanets are made of. Since we cannot travel to these worlds or collect samples directly, scientists rely on indirect methods. The most common approach is to study how a planet affects the light of its parent star. These small variations in brightness and movement can reveal astonishing details. Every fluctuation becomes a clue to the planet's nature. The first method is called the transit method. When a planet passes in front of its star, it blocks a tiny fraction of light. By carefully measuring this dip in brightness, scientists can estimate the planet's size. If repeated consistently, the data confirms that the dimming is due to a planet and not random noise. This technique has been used by telescopes like Kepler to discover thousands of exoplanets. For 55 Cancri e, transits revealed its incredibly short orbit and unusual density. Another key technique is the radial velocity method. This approach detects the small wobble of a star caused by the gravitational pull of its planet. By observing shifts in the star's light spectrum, astronomers can measure its movement. From this, they infer the planet's mass and orbit. When combined with transit data, it becomes possible to estimate density. Density, in turn, suggests whether a planet is rocky, gaseous, or something stranger. Spectroscopy is another powerful tool. When starlight passes through a planet's atmosphere, specific wavelengths are absorbed by different elements. By analyzing the spectrum, scientists can detect the presence of molecules like hydrogen, water vapor, or carbon dioxide. For planets like 55 Cancri e, spectroscopy provides hints about chemical composition. While the data is still limited, it allows scientists to make educated guesses about what lies beneath the surface. Of course, these methods are not perfect. The distance and brightness of the star play critical roles in how much data can be collected. Many signals are faint and can easily be confused with other cosmic phenomena. This is why astronomers use multiple techniques to confirm results. The case of 55 Cancri e is a prime example, as its classification relies on overlapping evidence from transit, radial velocity, and density measurements. The interpretation of this data requires complex models. By comparing observed numbers to computer simulations, scientists can test possible compositions. For 55 Cancri e, models suggested a carbon-rich interior, leading to the diamond planet theory. While models are never exact, they provide frameworks to explore possibilities. Each model narrows the range of what could be true, guiding future observations. These discoveries highlight the creativity of astronomy. Scientists are essentially solving puzzles with only fragments of information. They must combine physics, chemistry, and observation to build a coherent picture. Every planet is a unique case, requiring new adjustments to theory. This makes the field dynamic and full of surprises. Exoplanet science has grown into one of the most exciting frontiers of modern research. As technology improves, our ability to determine planetary composition will expand. The James Webb Space Telescope, for example, is designed to analyze atmospheres with unprecedented precision. Such instruments will allow us to test theories about worlds like 55 Cancri e more directly. They may confirm or refute the diamond planet hypothesis in the near future. With each advancement, our picture of distant worlds becomes clearer. It is worth noting how extraordinary this is. From Earth, we can analyze a planet dozens of light years away with nothing but light. This is a testament to the power of physics and human ingenuity. Every observation pushes the limits of what we thought possible. The fact that we can discuss the chemical makeup of an unseen world is itself astonishing. In the case of 55 Cancri e, these methods combine to suggest a planet unlike any other. Its density, orbit, and inferred composition point toward a carbon-rich world. While confirmation is still pending, the techniques used to study it represent the cutting edge of science. They remind us that the universe is not only vast, but also knowable through careful observation. And that knowledge leads us directly to its host star, which plays an equally crucial role the star it orbits and its characteristics. The planet 55. Cancri e does not exist in isolation. It orbits a star known as 55 Cancri a, located in the constellation of Cancer. This star is visible with modest telescopes and is relatively close in galactic terms, just 40 light-years from Earth. Classified as a G-type main sequence star, it is somewhat similar to our Sun. However, its system is far more complex than the solar system we know. 55 Cancri a is part of a binary star system, meaning it has a companion star. This makes its planetary system especially intriguing, as planets must orbit within the gravitational influence of two stars. Despite this complexity, the system hosts at least 5 confirmed planets. They range from gas giants to rocky super-Earths like 55 Cancri e. This diversity makes the system a goldmine for astronomers. The star itself is slightly smaller and cooler than the Sun, but still stable enough to support planets. Its brightness and proximity make it an excellent target for study. Observations of 55 Cancri A have helped refine measurements of its planet's orbits and masses. Without this star's cooperative nature, our understanding of the system would be much more limited. The star provides the light that reveals its planet's secrets. The orbit of 55 Cancri E is incredibly tight. The planet circles its star at a distance of only 0.0015 astronomical units, which is about 25 times closer than Mercury is to the Sun. As a result, the planet is locked in an inferno of heat and radiation. Temperatures on its surface soar to thousands of degrees. The extreme proximity means that 55 Cancri E is tidally locked, with one side always facing the star. This creates drastic differences between its permanent day and night sides. The star's influence is not just about heat. Its radiation likely strips away much of the planet's atmosphere. However, some data suggest that 55 Cancri E may still have a thin, volatile envelope. Understanding how the star affects this atmosphere is a major focus of current research. The interplay between starlight and planetary chemistry shapes the evolution of worlds. 55. Cancri E is a living experiment of this interaction. Other planets in the system provide fascinating comparisons. While 55 Cancri E orbits dangerously close, gas giants lie farther out. These massive worlds show how diverse a single planetary system can be. The contrast between them raises questions about how such a system forms and evolves. Why do some planets become giants while others remain rocky? The answers may lie in the star's composition and history. The presence of 2 stars in the system adds another layer of complexity. While 55 Cancri E orbits the primary star, the secondary star's gravity may influence the system as a whole. Such dynamics can shape orbital paths and stability. For astronomers, this makes the system a valuable test case for models of planetary behavior in binary environments. It reminds us that not all planetary systems are as simple as our own. Studying 55 Cancri A also helps place 55 Cancri E in context. By analyzing the star's chemical makeup, scientists infer what materials were available during planet formation. The star shows higher levels of carbon than the Sun, supporting the theory of a carbon-rich planet. This link between stellar chemistry and planetary composition is a key insight in exoplanet research. Stars and planets are deeply connected, sharing the same cosmic origins. The star's relative stability has been a blessing for astronomers. Unlike variable stars that flicker unpredictably, 55 Cancri A offers steady light for measurement. This consistency is essential for detecting small planetary signals. It has allowed scientists to gather high-quality data over decades. Without such stability, our knowledge of 55 Cancri E would be far less complete. Ultimately, the star 55 Cancri A is the stage upon which the drama of the diamond planet unfolds. Its light, gravity, and chemistry shape the world orbiting so closely to it. Understanding the star is as important as studying the planet itself. Together, they form a system that continues to challenge and expand our knowledge of the cosmos. And as we learn more about the star, we also prepare to uncover the secrets buried deep inside its most famous planet. The size and mass of 55 Cancri E compared to Earth. When astronomers describe 55 Cancri E as a super-Earth, they mean that it is larger and more massive than our planet, yet still rocky in nature. Measurements suggest it is about twice the diameter of Earth. Despite this, it is 8 times more massive, making it far denser than our own world. Such numbers immediately raise questions about its interior structure. Clearly, this is no ordinary rocky planet. The density of 55 Cancri E is one of the strongest clues to its composition. With a density significantly higher than Earth's, scientists infer that it must contain heavier elements. On Earth, density comes primarily from iron in the core and silicate rocks in the mantle. For 55 Cancri E, a carbon-rich composition may explain its unusual readings. Such density would allow for vast amounts of carbon compressed into diamond-like forms. In terms of gravity, a person standing on 55 Cancri E would feel much heavier than on Earth. Its higher mass means stronger gravitational pull. Although no human will ever stand there due to extreme conditions, the comparison helps us understand its scale. Walking on such a surface, if solid, would be nearly impossible under its crushing weight. These conditions are part of why the planet fascinates scientists and the public alike. The size and mass also influence the planet's temperature and geology. Being larger means more gravitational energy and pressure inside. This could drive unique geological processes unseen on Earth. Some models suggest intense volcanic activity fueled by its internal structure. If the planet's surface is constantly reshaped by lava and heat, it may look completely alien compared to our home world. For comparison, Mercury is only 38% the size of Earth, and yet its density is close to Earth's. Jupiter, meanwhile, is 11 times larger but is mostly gas, with a much lower density. This contrast shows how size alone does not define a planet's nature. It is the combination of size and mass that reveals the truth. In the case of 55 Cancri E, both are extraordinary, pointing to a world of extremes. Another intriguing factor is the balance between its small orbit and large mass. Orbiting so close to its star, a smaller, lighter planet might have been stripped away by radiation. Yet 55 Cancri E endures, suggesting a toughness built from its dense interior. Its survival so near its star may be due to this unusual composition. If true, this resilience further supports the theory of a planet rich in carbon and diamond. The comparison with Earth also deepens our appreciation of our planet's uniqueness. Earth is perfectly balanced in size and mass to sustain life, with moderate gravity and a stable crust. By contrast, 55 Cancri A reminds us that not all rocky planets are welcoming. It is a stark example of how different worlds can be, even when they share some similarities. The term super-Earth does not mean more habitable, it means more extreme. As scientists refine their measurements, the exact numbers for size and mass may shift slightly, but the general picture remains the same: a dense, heavy, superheated planet far different from Earth. This reinforces the idea that rocky planets come in many varieties, some far stranger than what we imagined. 55. Cancri E continues to push the boundaries of planetary classification. The extraordinary mass and density also play a role in the diamond planet theory. If much of its mass is made of carbon, the pressures inside would naturally form diamonds. This makes its physical size more than just a statistic. It becomes evidence of its possible glittering core. The more we learn about its size and density, the more the diamond hypothesis seems plausible. Ultimately, comparing 55 Cancri E to Earth highlights just how diverse planets can be. Our homeworld may seem typical, but in the wider universe it may be the exception. 55. Cancri E is a reminder that Earth-like does not always mean Earth twin. Instead, it represents an entirely new category of rocky super-Earths. And to understand how such a planet came to exist, we must explore the formation of carbon-rich worlds. The formation of carbon-rich planets. The idea of a carbon-rich planet like 55 Cancri E challenges our understanding of planetary formation. In our solar system, most rocky planets are made of silicates, with oxygen as the dominant element. But around stars with higher carbon content, the recipe for planets may change. Instead of silicate-dominated rocks, carbon compounds can dominate. This difference leads to exotic possibilities, including diamond-rich interiors. Stars and planets form from the same cloud of gas and dust. The elements present in that cloud determine the types of planets that emerge. If a star has more carbon relative to oxygen, the resulting planets may follow a different path. In the case of 55 Cancri A, studies suggest it has a higher carbon-to-oxygen ratio than the Sun. This increases the likelihood of planets like 55 Cancri E forming with unusual chemistries. In such environments, instead of silicon-based rocks like granite or basalt, planets may form with carbides and graphite. Over time, under intense pressure, graphite can transform into diamond. If this process occurs on a planetary scale, the result is astonishing: a world where diamonds are not rare gems but structural building blocks. This idea redefines what we imagine when we picture a rocky planet. The role of temperature and location during formation is also critical. Planets closer to their star experience different chemical processes than those farther away. For 55 Cancri E, forming so near its star may have locked in high carbon content early on. The intense heat could have stripped away lighter elements, leaving behind heavier carbon-based materials. This would further enrich its diamond-like potential. Simulations of planetary systems show that such outcomes are rare, but possible. The diversity of exoplanets discovered so far supports the idea that no two systems are alike. Some worlds are covered in oceans, others in gas, and some, like 55 Cancri E, may be built from carbon. Each discovery expands the boundaries of planetary science. Theories evolve as new data forces us to rethink what planets can be. The possibility of carbon-rich planets has major implications. It means the universe may contain countless exotic worlds we have yet to imagine. Some might have black reflective surfaces from carbon compounds. Others might shimmer with crystalline structures beneath the crust. Such worlds are not just science fiction. They are real possibilities based on physics and chemistry. Understanding carbon-rich planet formation also sheds light on Earth's uniqueness. Our balance of oxygen and carbon produced conditions favorable for life. A diamond planet, by contrast, may be beautiful but hostile. Its surface would be scorching, its atmosphere toxic, and its geology alien. This contrast helps us see how delicate the conditions for habitability really are. For scientists, the study of such planets also provides clues about galactic history. The distribution of elements in stars tells us about past generations of supernovae. If carbon-rich planets are more common in certain regions, it reflects the chemical evolution of the galaxy. Thus, studying 55 Cancri E connects planetary science to cosmic history. The theory of carbon planet formation is still developing. More data from telescopes will be needed to confirm these ideas. But the fact that such planets are possible is revolutionary in itself. It proves that our models of planet formation must account for extreme diversity. No longer can we assume that Earth is the template for rocky planets. Ultimately, the formation of carbon-rich planets like 55 Cancri E expands our imagination of the universe. They show us that nature is far more inventive than we are. While Earth gave us oceans, forests, and life, other planets may give us diamonds, carbon skies, and fiery landscapes. This diversity is what makes the study of exoplanets so endlessly fascinating. The role of pressure and temperature in the creation of diamonds on Earth. Diamonds are formed deep within the mantle, where immense pressure and heat compress carbon atoms into crystal structures. These conditions are extreme, existing more than 150 kilometers beneath the surface. Over millions of years, volcanic activity carries these diamonds upward. This natural process demonstrates how pressure and temperature transform carbon into one of the hardest substances known. But on 55 Cancri E, the scale is far greater. The planet's enormous mass and density mean that pressures inside it are far stronger than anything on Earth. Combined with its extreme heat, these conditions could create vast layers of crystallized carbon. Instead of small deposits like on Earth, entire regions of the planet's interior might consist of diamond. In this sense, the planet acts as a cosmic pressure chamber, constantly forging precious structures deep within its core. Temperature is another critical factor. Surface temperatures on 55 Cancri E reach thousands of degrees, hot enough to melt metals. Inside, conditions are even more severe. Such heat helps carbon atoms move into the stable crystal lattice that forms diamonds. The balance of high heat and overwhelming pressure makes the diamond planet theory scientifically plausible. While Earth produces diamonds sparingly, 55 Cancri E may do so on a planetary scale. What makes the situation even more fascinating is the possible combination of graphite and diamond within its structure. Graphite is another form of carbon, soft and layered compared to diamond's hardness. At lower pressures, graphite may dominate, but as one moves deeper, graphite transforms into diamond. This layered arrangement could make 55 Cancri E unlike any world we know. Its geology may consist of exotic strata of pure carbon. The creation of diamonds under such conditions challenges our understanding of geology. On Earth, the mantle is a mixture of silicates, oxides, and metals. On 55 Cancri E, carbon dominates, producing completely different physical processes. Such differences highlight how alien this world is. It also raises questions about whether similar planets might exist elsewhere in the galaxy, waiting to be discovered. Scientists are cautious, however, because direct evidence is still lacking. No telescope can yet peer into the interior of a distant planet. Instead, models based on density and stellar chemistry provide the framework for these theories. While compelling, they remain hypothetical. Future instruments may confirm whether Diamond truly forms deep inside 55 Cancri A. Until then, the Diamond planet remains both a scientific mystery and a captivating idea. The role of pressure and temperature is also tied to the planet's dynamic environment. Extreme heat from its star could contribute to unusual geological activity. Volcanism may release carbon compounds onto the surface, reshaping the planet over time. If true, the planet may not only be filled with diamond, but also coated in exotic minerals created under high heat. This paints an image of a fiery, glittering world. The creation of diamonds on such a scale has implications beyond geology. It suggests that precious stones, so rare on Earth, could be common in other parts of the universe. What is valuable here may be abundant elsewhere. This forces us to reconsider our definitions of rarity and worth. From a cosmic perspective, diamonds might not be treasures at all, but natural byproducts of certain planetary environments. These conditions also show how fragile Earth's balance is. Our planet has just the right conditions to produce resources we value without overwhelming us with extremes. In contrast, 55 Cancri E shows what happens when conditions are pushed to their limits. The result is a world so alien that it is almost impossible to imagine living there. Yet it exists, proving that nature can produce planets beyond our wildest imagination. Ultimately, the role of pressure and temperature in diamond formation illustrates the connection between physics and beauty. The harshest conditions in the universe can create dazzling structures of unimaginable scale. 55. Cancri A may be inhospitable, but its very existence reminds us of the creative power of natural laws. Diamonds, on Earth or on distant planets, are proof that even in extremes, order and beauty can emerge. Differences between 55 Cancri E and planets in the solar system. At first glance, 55 Cancri E might be compared to rocky planets like Earth, Venus, or Mercury. But the differences quickly overshadow the similarities. For one, its orbit is incredibly close to its star, much closer than Mercury is to the Sun. This proximity creates conditions far more extreme than anything in the solar system. Its year lasts less than 18 hours compared to Earth's 365 days. Such a rapid orbit makes it fundamentally different from our own planets. Surface temperature is another striking difference. Mercury, the hottest planet in our solar system, reaches up to 430 degrees during the day. Venus, with its greenhouse atmosphere, climbs even higher, up to 470 degrees C. But 55 Cancri E dwarfs both, with temperatures exceeding 2,000 degrees C. At such levels, metals can vaporize, and rocks may partially melt. This is a world where Earth's geology would be unrecognizable, and human survival is impossible. Composition is another key contrast. Earth and its neighbors are silicate-based, with oxygen-rich minerals dominating. By comparison, 55 Cancri E may be carbon-based, forming a completely alien geology. Imagine a world where diamond and graphite replace granite and basalt. This fundamental shift in chemistry makes 55 Cancri E a category of its own, beyond any example in our solar system. The planet's density also sets it apart. Earth's average density is about 5 grams per cubic centimeter, while 55 Cancri E's density suggests something heavier and stranger. This reflects its possible diamond-rich interior, which Earth cannot match. Even compared to Mercury, known for its dense metallic core, 55 Cancri E is in a class of its own. Its density alone makes it one of the most extraordinary planets ever studied. Atmosphere is another area of difference. Venus has a thick, toxic atmosphere, while Mars has a thin, tenuous one. For 55 Cancri A, the story is uncertain. Some studies suggest it may have a thin envelope of gases, while others indicate it could be bare. Radiation from its star constantly bombards it, likely stripping away lighter gases. Whatever remains is certainly hostile, nothing like Earth's breathable air. Habitability is also starkly different. Earth is perfectly suited for life, with liquid water, stable temperatures, and a protective atmosphere. 55 Cancri E, on the other hand, is a blazing inferno. Its surface is too hot for water, its atmosphere likely toxic, and its radiation levels extreme. The comparison emphasizes how rare Earth-like conditions truly are. In cosmic terms, Earth may be a rare oasis, while most planets are hostile like 55 Cancri A. The day-night cycle also adds contrast. Earth rotates every 24 hours, creating day and night. 55 Cancri A, being tidally locked, always shows the same face to its star. One hemisphere is scorched in perpetual daylight, while the other is frozen in eternal night. This creates dramatic contrasts that no planet in our solar system experiences so severely. The result is a world of extremes, with no middle ground. Geology may also differ radically. On Earth, tectonics and erosion shape the surface. On Venus, volcanic activity dominates. On 55 Cancri E, the heat and pressure could drive exotic volcanism unlike anything we know. Some studies suggest molten lava flows may cover parts of the planet. Imagine a surface glowing with fiery rivers of liquid rock, completely alien compared to Earth's landscapes. In terms of scale, Earth is balanced in mass, orbit, and composition, making it habitable. 55 Cancri E pushes every parameter to the extreme. Its short year, high temperature, exotic chemistry, and possible diamond interior make it utterly unique. Comparing the two highlights the diversity of planets in the universe. It shows that what we consider normal is not the rule, but the exception. Ultimately, the differences between 55 Cancri E and solar system planets reveal how varied worlds can be. Earth offers comfort and balance, while 55 Cancri E represents extremes of heat, pressure, and composition. By studying such differences, scientists learn more about the possibilities of planetary evolution. It is through these contrasts that we understand both the rarity of Earth and the abundance of alien worlds. Other discoveries of exotic exoplanets. 55 Cancri A is not the only bizarre world that astronomers have uncovered. The universe is filled with planets that defy expectations and challenge our imagination. One of the most famous is HD 189733b, a gas giant where it literally rains glass. Winds on this world blow at thousands of kilometers per hour, flinging shards of glass sideways through the atmosphere. It is a violent, glittering storm unlike anything we could ever experience on Earth. Another extraordinary planet is WASP 12b, a so-called hot Jupiter that orbits so close to its star that it is being ripped apart. The gravitational pull of its star is slowly tearing the planet into pieces. Over time, its atmosphere is being consumed, leaving behind only remnants. This shows how destructive the relationship between star and planet can be, especially in extreme orbits. It reminds us that not all planets survive the passage of time. Kepler 22b, on the other hand, excites scientists for an entirely different reason. This planet lies within the habitable zone of its star, meaning liquid water might exist on its surface. It is much larger than Earth, but its location raises the possibility of life. Although no evidence of habitability has been confirmed, the idea of an ocean world teeming with unknown forms of life continues to spark scientific curiosity and public imagination. There are also planets like TRIES 2b, often called the darkest planet ever found. It reflects less than 1% of the light that hits it, making it blacker than coal. Scientists are still trying to understand why its atmosphere absorbs almost all light. The discovery proves that not all planets shine or sparkle. Some are invisible even when orbiting brightly lit stars. This extreme darkness is as fascinating as the glitter of the diamond planet. Gliese 1214b is another exotic example, sometimes referred to as a water world. Evidence suggests it could be covered in a deep global ocean, with no land at all. If true, its surface would be dominated entirely by water under high pressure. Beneath the ocean, strange forms of ice could exist, unlike anything seen on Earth. This highlights how varied planetary environments can be. from fiery infernos to endless seas. Some planets orbit 2 stars instead of 1, creating skies with double sunsets like in science fiction. Kepler 16b is a famous example, orbiting a binary star system. This discovery showed that such circumbinary planets are not just fantasy, they are real, stable worlds, proving that planetary systems can form in astonishingly diverse environments. Such discoveries continue to expand our idea of what a planet can be. Even rogue planets have been detected, worlds that drift through space without orbiting any star. These lonely wanderers are frozen and dark, moving silently across the galaxy. Some may have once belonged to solar systems, only to be ejected by gravitational interactions. Their very existence shows that planets are not bound to stars forever. The cosmos is full of planetary orphans, endlessly traveling the void. Each exotic exoplanet discovered helps refine our understanding of the universe. They teach us that planetary systems can be wildly different from our own. While Earth feels normal to us, the truth is that normal is hard to define. The range of possibilities is staggering, from glowing lava worlds to frozen giants of ice and gas. Each discovery makes the universe feel richer and stranger than before. These exotic worlds also highlight the creativity of nature. Just as life on Earth evolved in countless forms, planets emerge in endless variations. Every new discovery pushes science forward, forcing us to rethink old assumptions. Exotic exoplanets are not just curiosities, they are crucial pieces of the cosmic puzzle. They tell us that the universe is filled with surprises beyond our imagination. In this context, 55 Cancri A is part of a much larger story. It is one of many planets that expand the boundaries of possibility. Its diamond-rich hypothesis may be unique, but it shares the same spirit of wonder with all exotic discoveries. Each of these planets shows us that reality can be stranger than science fiction. Together, they remind us that the universe is endlessly creative, offering mysteries that may take centuries to unravel. What still remains to be discovered about this mysterious planet? Despite everything we know about 55 Cancri E, many questions remain unanswered. The diamond planet theory is still only a hypothesis, and direct evidence is lacking. We have inferred its composition from density and stellar chemistry, but confirmation requires more precise data. Future telescopes, like the James Webb Space Telescope, may provide critical insights into its atmosphere and surface. Until then, the diamond world remains partly in the realm of speculation. One major mystery is the nature of its atmosphere. Some observations suggest it may have a thin envelope of gases, possibly including hydrogen or helium. Others argue that intense radiation from its star would strip away any atmosphere quickly. If an atmosphere exists, it could hold vital clues to the planet's evolution. Understanding this would help scientists decide whether the diamond planet theory holds up. Another unanswered question is the planet's internal structure. Is it truly filled with carbon, or are other elements present in large amounts? Without direct sampling, this is impossible to confirm. Advanced models and simulations may bring us closer, but uncertainty remains. The challenge of peering into a planet dozens of light years away makes this one of the greatest puzzles in modern astronomy. The surface of 55 Cancri E also remains a mystery. Some theories suggest molten lava may cover parts of it, creating glowing rivers under the blazing heat. Others imagine a solid crust of exotic minerals. Observing such details from Earth is extremely difficult. However, each new generation of telescopes sharpens our vision, bringing us closer to answers. The surface may hold surprises that even current theories cannot predict. The role of its star adds further complexity. How does constant radiation shape the planet's evolution? How stable is its orbit over time? These questions are tied to larger studies of exoplanetary systems. By learning more about 55 Cancri E, we also gain insight into how stars influence the worlds around them. Its closeness to its star makes it an extreme case, but one worth studying. There is also the question of habitability. While current evidence suggests conditions far too hostile for life as we know it, we cannot completely rule out exotic forms of chemistry. Could some unknown process allow stability in such a place? Though unlikely, even asking the question expands our imagination. Studying uninhabitable worlds helps refine the definition of what life-friendly conditions truly are. The diamond planet theory itself will continue to be tested. As more precise measurements are made, the picture of 55 Cancri E may change. It might turn out to be less diamond-rich than expected, or even something completely different. Whatever the outcome, the pursuit of truth will deepen our understanding of planetary diversity. Science thrives on such revisions, turning uncertainty into discovery. Another exciting frontier is the possibility of direct imaging. While currently beyond our reach, future space missions might one day capture actual images of 55 Cancri E. Seeing its glowing alien surface would be a profound step forward. Such data could confirm theories that today remain speculative. Humanity is inching closer to technologies that could make this dream a reality. The mysteries of 55 Cancri E also connect to larger questions about the universe. How common are carbon-rich planets? Are diamond planets rare jewels or abundant across the galaxy? Answering this could reshape our view of planetary formation. It could also reveal whether Earth-like conditions are the exception or the rule. The search for these answers keeps astronomers looking to the stars. Ultimately, what remains unknown about 55 Cancri E is as important as what we know. The planet stands as a reminder that discovery is an ongoing process. Its dazzling potential captures our imagination, but its secrets keep science alive. The diamond planet may or may not be filled with gems, but it is certainly filled with mysteries. And solving them will take us deeper into the story of our universe.